Okay. So let's talk about Regio and Stereoselectivity. Okay, and I gave you the table, and I think everything's there, but again, it would be better if you made up your own table or at least modified the one that I gave you. So the table of all the reagents and how they add, and for those of you that didn't come, sucks to be you because you're just not getting that table. Or it's in the folder. So, and then also we'll talk about the sort of this. I just came up with a quick flow chart to talk about whether reactions are regio or stereoselective. So, if we're looking at regio and stereoselectivity, again, just to go back to yesterday, the first part for both of these is selectivity. And so what selectivity means is that we're going to have more than one possible product, and the reaction has a major product. And it's not 50-50 in terms of products or equal percentages across the board. So for a reaction to be selective, if you only have one product, you're not selective. If you don't have a major product because everything is 50-50, you're not selective. So it's going to be as easy to say when is this not selective as it will be to say when it is selective. So that's going to be our issue, is we're going to have to write the possible products, and then if there's a major product, then that would be selective. The difference in these two is regio versus stereo. So if we start with regio, the idea here is that those products that we're having a major product from, the products are structural isomers, which means they're attached differently and they ultimately have different IUPAC names. And the way we're going to get those two products is from the reaction being Markovnikov and anti-Markovnikov. So when we're talking about anti-Markovnikov and anti-Markovnikov addition, that's leading to the regio selectivity of the reaction. When we're talking about 100% cis, trans, or 50-50, that's going to lead to stereoselectivity. Okay, so I'll just define regio and then we'll come back to stereo selectivity. So when is the reaction not going to be not going to be regio selective? You're not going to be regio selective when the reagent basically adds the same groups to each carbon. And that's what I call a symmetrical reagent, or a symmetric reagent is what it should be called. And so if you go back and you remember which reagents add the same things, or if you look at your chart, you will see that that's reagents like Br2, all of the cis hydroxylation reactions, as well as when you add hydrogen. So those add the same thing, and if you're adding the same thing, you're only going to get one product. So therefore, those cannot be regioselective by definition. Okay. So you won't have a regioselective BR2 addition. You could end up with BR2 and water addition, but there's a couple pages that might be helpful. You could add BR2 and water because then you're adding two different things, but if you're adding the same thing, it can't be regioselective. That would be the same thing as saying that the reaction is neither Markovnikov nor anti-Markovnikov. So on the chart where it says neither, you'll see it says neither because of the reagents that are symmetrical. So that can't be regioselective. Also, when you have a double bond that has symmetry to it that is symmetric, if the alkene is symmetrical, then that also cannot be regioselective. Because it doesn't matter whether, if I'm adding an H and an OH to that double bond, it doesn't matter whether I add the H to the top, the OH to the bottom, or vice versa, simply because I'm going to get the same product either way. So when you have a symmetrical alkene, it will not be regioselective, regardless of the reagent that you're using. Okay. So again, sometimes it's easier. I could have made the flow chart being basically negative, I guess, in terms of if it's this, then it's no, and I kind of did that. But that's kind of our screening. So as you look at a reaction, the first thing, if it's the same group, can't be regio. If the alkene is symmetrical, it can't be regio as well. But you have to take every reaction case by case when you're talking about regioselectivity. And I haven't moved, and I will move the folder with all of there's a lot of homework problems that was from a week from last Friday. I'm going to move those problems in because what I did was I kind of systematically said, okay, take cyclohexene and react it with our reagents. Write the major product, tell me if it's regio, stereo, both, or neither. Then I took and I put one methyl group on it. And then I took and put two methyl groups on it. And then I put a methyl and an ethyl group on it. So I did all of the cyclic compounds. I'm sure the book does some acyclic compounds as well, but the rules are pretty much the same. So every one of these is going to have a slightly, or could have a slightly different answer. So you really have to take these one by one and apply those rules. Okay. So if it's symmetrical for either reagent or alkene, can't be regioselective. So the question is, when will it be regioselective? And let's take, as an example, let's take this methyl cyclohexene. And let's add a reagent to it that's not symmetrical. So, what reagent do you want to add to it that's not symmetrical? Give me a reagent. HBr, okay? All right, so if we add HBr to this double bond, how many possible products do we have? Well, I could add the H to the top carbon and the Br to the bottom carbon, or I could add the Br to the top carbon and add H to the bottom carbon. All I've done here is write what products? The Markovnikov and the anti-Markovnikov product. But my first question is, these are two possible products. We're going to get to, well, let me just say right now that possible doesn't mean that that's the major product. It just means it's a possible product. Normally it means the minor product, but let's say I had a primary system in here so that I would be writing a primary carbocation. We know we wouldn't get any of that product. But the people who came up with stereo and regio selectivity, and I don't know who those were, but they were back in the 50s, they didn't make a distinction between 5149 and 100 to 0. So if a product is possible but it's not formed, it's still possible. So 100-0 is just as selective as 51%, 49%. And that's something I wish they would take up consideration of, but they're not going to. So there is no term that would designate that it's 100-0. My term would be specific, but stereo-specific means something totally different. Kaylee?
So 100% to 0 is stereo-selective, but 50-50 wouldn't.
Right. Right. You have to have a majority of one product. And that's the one we need to deal with, is stereoselectivity, because we know we had 2 BRs trans, but adding the 2 BRs cis is still possible. For all these regioselectivities, like I said, unless it's a primary carbocation, you know you're going to get some of that product. It's not forbidden. The 2 BRs cis would be forbidden, but it's not forbidden. It's just possible but not formed. So that's something we have to deal with. So in this case, what's the major product? The major product is the Markovnikov product, which would be A or B. Which one of those two is the major product? I hear very weak B's.
B.
That's assertive. That's what we want. It is B. It's B, because the hydrogen added to the carbon with the most hydrogens in the double bond, which is the bottom one, and the BR added to the top one.
Is that a rule based on the reagent we used?
Yes. So remember, HBr was Markovnikov because I'm adding H plus to the double bond, and I have to add the H plus to the carbon with the most hydrogens because that's the only way I'm going to get the most stable carbocation. Because the most stable carbocations then can be on the carbon with the least amount of hydrogens, which is the most substituted one. So that's why in the chart you'll have to know what's the major product. Now you can always write both products by simply flipping the reagent, flipping what you're adding, but you need to know what the major product is. So B is the major product. So in this case, does this fit selectivity? I have 2 products, check. They are structural isomers because one is 1-bromo-2-methyl cyclohexane and the other one is 1-bromo-1-methyl cyclohexane, so those are different structures. And the different structures always arise because of Markovnikov, anti-Markovnikov, as long as the system isn't symmetrical. Then we have 2 products, 2 structural isomers. Did the reaction select one over the other? Yes, because this is Markovnikov and the Markovnikov products formed. So this one would be classified as regioselective. But let me change that. So how about I put a methyl group and an ethyl group? And let's do the same reaction. When I ask you these questions on the exam, just like in that problem set, I'm going to say write the major product of the reaction and tell me whether the reaction is regio, stereo, both, or neither. Right now, we're just dealing with regioselectivity. So I would write my 2 possible products if, at least at this point, I'm going to add my H to the top, BR to the bottom, and then I'm going to reverse that and add Br to the top and H to the bottom. So there are my two products. Check, two products. Different products? Structural isomeric products? Yes. This wasn't a symmetrical alkene, so in general, if it's not symmetrical, you'll get two different products. Okay. Final checkbox that has to be hit for this to be regioselective is major product. So what's the major product of this reaction? Again, according to Markovnikov's rule, which says that the hydrogen goes to the carbon with the most hydrogens.
A.
I like the aggressiveness. So you're going to withdraw that answer?
Think about it.
What'd you say?
They have the same amount of hydrogen.
So carbons A and B up here have the same number of hydrogens, which is 0. So since they have the same number of hydrogens, what happens to A and B? They're 50-50 or they're both. You could call both of them the major product. There's no, the way I wrote it on the flow chart was I said there is one singular major product. In this case, there is not one singular major product. So both of these would be formed at a 50-50 ratio. Kaylee?
I'm confused because on the chart, they have the HBr as a reagent as anti-Markov.
It should be there should be an HBr with a peroxide.
Okay.
Is that not?
Yeah, HX would be HBr. Okay.
So HX is where HBr is.
So HBr with hydrogen peroxide here.
So HBr and hydrogen peroxide would be anti-Markovnikov.
Sorry.
That's the one we just did yesterday, going through the radical intermediate. So yeah, I just put HX because it's HCl, HBr, HI.
Sorry.
No, that's okay. If you're using my chart, you have to understand the way I wrote it, which is why it's always better if you modify this to the way you think, it'll stick longer. So if you want to write your own chart and then compare, you can always do that. But I figured I'll put the chart together and then shame people that didn't come today. Or the morning class because I didn't have it printed out yet. Okay. So this is 50-50, no major product, therefore no selectivity. So this one is not regioselective. Okay. So whether you remember for these kinds of problems, it's better to just be able to write the product without having to go through the mechanism. But if you have to go through a bit of the mechanism to get to the final product, that's okay. But that's why I'd like you to remember what is being added so that you can just quickly write these products, because you need the products in order to figure out if it's regio or stereoselective.
So I know that for some of these we do have to know the mechanism, and for some of them we don't.
Yeah, I should have highlighted the ones. I should have highlighted the ones that you needed the mechanisms for. And let me do that at the end. Let me tell you which ones. Let me tell you which ones to write for that, because that was actually, you know what, I have that from the summer class on here that I can send out, but we'll do it at the end. Okay, so that's one that's regio, one that's not regio. So obviously the reaction has to favor Markovnikov or anti-Markovnikov, but then again, these reagents that we had here, those are the reagents that should show up as neither on the chart because they're symmetrical. Okay. So if you're looking at the flow, so if you're looking at this, so if you're looking kind of at the flow chart, it kind of just takes you step by step. But the steps would be is the reagent or the alkene symmetrical? If the answer is yes to either one of those questions, it's not regioselective. Then you write the two possible products. Is one favored by Markovnikov or anti-Markovnikov, depending on the reaction? And if the answer is yes there, then it's regioselective. Okay. So the flow chart may be kind of deceptively simple, but I want to make sure you understand the reasoning behind why it would work. Okay. All right, so everybody okay with that? So that's regioselectivity. So the next issue is, what does stereoselectivity mean? And for stereoselectivity, what we mean there is that, again, we're forming multiple products, we're selecting one, but in this case, what's the relationship between the two products? And that is, obviously, they are stereoisomers. What kind of stereoisomers? It's been a long semester. It's not over, right? When we come back, we're reaching the 2 and 3. No, we just have 2 weeks left. This Dr. Weaver told me when I took this job. He's like, well, the last 2 weeks, they're not really going to listen to you. And first of all, I'm like, I just came from OU, so nobody listened to me for 10 weeks there because we were on quarters at the time. So I'm kind of used to that. But I'm like, really? At John Carroll, nobody's going to listen to me in the last 2 weeks? And he goes, trust me, I've been here 45. He'd been here 45 years. So try not to fall into that. You should end your semester after your final. Ending before that can have detrimental effects. Right? But I know it's tough. But I digress. What kind of stereoisomers have we talked about this semester? We've talked about like cis-trans. What else? EZ. EZ specifically is with double bonds, and we're not doing anything with double bonds right now. Cis-trans could be the ring, whether they're cis or trans or not. What other stereoisomers do we have?
I don't know if RNS is one.
So what does RNS represent in enantiomers? If there's a single chiral center, then we would be talking about enantiomers. And then going along with enantiomers, there's diastereomers. So actually, it's enantiomers and diastereomers that are the most important if we're talking about stereoselectivity. Okay. So we need to make more than one possible stereoisomer, and we need to select it. So, and there's some rules here for that as well. Okay. So, in terms of the relationships here, are there some things that will never be stereoselective? Yes. In order to make, well, let me just say, when you make a racemic mixture, which is automatically a 50-50 mixture of enantiomers, it will never be stereoselective. Okay, so in terms of the not stereoselective, the first one is if your reaction makes a racemic mixture. Now, we can sort of broaden this out, although it's not quite the same. That also means that anytime we add something 50-50 cis and trans, it will not be stereoselective. So when I'm adding groups 50-50 cis and trans, I am by definition making both of at least the enantiomers, if not the diastereomers. Okay, so anything that's 50-50 will not be cis or trans. Now, you could go through the chart and you can see which ones are 50-50. They're the first three or first four, and they're all because the intermediate was either a carbocation or because it was a radical, which means that the intermediate was sp2 hybridized. So those always give 50-50, and so therefore they will not be stereoselective. Now, the rule in organic chemistry is this. You need an optically active reagent. You need something that's chiral, that's something that is it's a non-50-50 mixture in order to make a chiral product, meaning a product that is not 50-50. If you generate a product with a single chiral center, you will always get 50-50 unless a reagent was chiral to begin with. If you think about all the things we've done in lab, the only way we made the yeast product optically active in an unequal mixture of enantiomers was because the enzymes in the yeast were all of one-handed form. And so we had a chiral reagent that made a chiral product. If we would have done that reaction with another reagent that wasn't chiral, we would have gotten a 50-50 mixture. So anytime we do a reaction without a chiral reagent, we will get a 50-50 mixture, a racemic mixture. Okay. Another example of a reaction where we did have something chiral was SN2. Right? If I made a chiral product in SN2, it was because the reagent itself was chiral. So in these reactions, I'm trying to take a double bond, which isn't chiral, and I'm going to react it with reagents that aren't chiral. So therefore, anytime I make a chiral center, a single chiral center, it's always going to be 50-50 RNS. Okay? And it will not be stereoselective because it didn't select R over S, it's 50-50.
By reagent, do you mean like the HBr or like the alkene?
The HBr, the potassium permanganate, the HBr peroxide, hydrogen, any of those reagents, there is nothing chiral in them. Right? Now, some people might go, well, what if you add something chiral? Maybe you might get it, but we're not doing that. We're using achiral reagents. And the double bond itself can't be chiral. Okay. So that means that for me to make two stereoisomers that are not 50-50 in my mixture, if we just look at the number of chiral centers in the product, if you have 0 chiral centers in the product, forget about stereoselectivity. If you have 1 chiral center in the product, forget about stereoselectivity because that 1 chiral center will automatically be 50-50 RS. Unless I used a chiral reagent, I just dismissed that. We're not using a chiral reagent in these reactions. Okay? So that means in order for the reaction to stand a chance of being stereoselective, I need at least 2 chiral centers. So if you have 2 or more chiral centers, it may be stereoselective. Now, what's the maybe? It may be stereoselective if the reaction that we're doing is either 100% cis or 100% trans. So if the reaction's 50-50, you're not going to get stereoselectivity. And the reactions that were 50-50 all involve carbocations and radicals. Okay. So that means the first test is the reaction I'm doing 100% cis or trans? Then I do the reaction, I write the products. How many chiral centers did I have? If I had 2, it's stereoselective. If I have 0 or 1, it's not. Okay. That's why that flow chart is so short, because that really gets to the essential element of it. But we need an example. So let's do cyclohexene. What do you want to add to that that adds either 50 or 100% cis or 100% trans? What reagent do you want to do?
BR2.
Okay. So I'm going to add BR2 to the double bond. First question, is that regioselective? No, because the alkene is symmetrical and so is the BR2. So it is not regioselective. Is it stereoselective? Let's find out. So when I add the 2 BRs, and this is what the tricky part is. So when I add the 2 BRs to the double bond, my 2 possible ways of adding it are 100% cis, but I could also add it 100% trans. Or in other words, I could add it cis or trans. So these are my 2 possible products. There's actually, well, these are my 2 possible products for the moment. Okay. And which one's the major product? A or B? B? B is my product 100% of the time. And A is my product 0% of the time. But what I just said a few minutes ago was the people who did Regio and Stereoselectivity did not come up with a way or another name to describe something that's 100-0. They just said, oh, it's selective. Okay. So that's selective. Is A possible? It's possible. If we didn't know the mechanism, it would be possible, but it's not going to be formed. So do we have more than one possible product? Yes. Did we select one over the other? Yes, 100-0. Is the reaction stereoselective then? Yes. By the strict definition, I have 2 possible products. I selected one over the other. Oh wait, I guess we need one more thing. What's the relationship between A and B? What kind of stereoisomers are they? They're diastereomers because the top carbon has the same configuration, the bottom carbon has the opposite configuration. Therefore, these 2 are diastereomers, so therefore they are stereoisomers. So this reaction has the possibility of forming 2 stereoisomers, and it has selected one 100-0. Because remember, it goes through the triangular intermediate. So the bromine sits on top, and then the other bromine adds underneath. Right? So this is a stereoselective reaction.
So for the stereoselective one, the products have to be 100% one or the other to be stereoselective. But for the regioselective one, is that the same? Because they can't be 50-50.
So actually, they don't really need to be 100-0. It's just those are the only examples we have. All the addition reactions we've done have either been 100% cis or 100% trans or 50-50. There's been nothing in between.
So the only differentiation then for these two, Regio and Stereo, is that stereoselective, based on our loose definition, has to be 100-0, and Regio can be anything as long as it's not 50-50?
Right. So the Regio deals with Markovnikov and anti-Markovnikov. So in most cases, you got a secondary versus a tertiary carbocation in the mechanism. Secondary carbocations are stable, so you're going to get a little of that product. So it's always, in that case, you're going to get both. But in these mechanisms, it was either all or nothing. If it was 80-20, it would still be selective. It would still be stereoselective. We just don't have any reactions that do that. Okay, everybody kind of still okay with that? So then if you look at sort of the criteria, we can actually boil it down so you don't have to do that each time, although you can. You could certainly say, oh, I'm going to write my two products. Are they stereoisomers? And they have to be diastereomers, because if they're two enantiomers, automatically 50-50. If they have no chiral centers, they are the same product. So they got to have two chiral centers. In this case, how many chiral centers do we have? We have two chiral centers. So if I applied the flow chart to this, I would say, number one, does BR add 100% cis or trans? Yes, it adds 100% trans. In my product, did I make two chiral centers? Yes. Stereoselective. So we can look at it from either way.
So if they are enantiomers, they're not stereoselective?
Right. If you make enantiomers, we always make enantiomers in 50-50, in a 50-50 ratio. Unless there was something over here that was chiral in the reagents, and there isn't. All right, let's make it methyl cyclohexene. Give me a reagent other than Br2 that adds 100% either cis or trans. What I hear?
KMNO4 and OH minus.
Choose another one.
So water.
Water. Which one with water? BH3. BH3 and H2O2. Hydroboration oxidation. We can do the KMNO4 and hydroxide, but I wanted something with, I wanted one of those two. So I shouldn't probably let you choose, but if I rejected them all, then we'd get to that point. All right, what is BH3 and H2O2 adding? H and OH how? Markovnikov, anti-Markovnikov. Anti-Markovnikov, which means in this case the H would attach to the carbon with the CH3 and the OH would attach to the other one, to the other carbon. Okay. Now I'm just writing the major product for the major product as far as the Regio selectivity goes. The product as far as the non-Regio, or as far as the Regio selectivity, this is the other possible product adding the H and the OH. No, I just haven't put in my bold and dashed wedges because that's the next thing I'm going to do. Okay. So H and OH add 100% cis. So we'll give them both bold wedges. Does it matter? No. Okay, so there are my two possible products as far as Regio selectivity goes. Is this reaction regioselective? As far as the placement of the H and the OH goes, did I make two structural isomers? Yes. Am I favoring one over the other? Yes, because that's the major product. So this reaction is regioselective. The Markovnikov and anti-Markovnikov products are different, and I selected the anti-Markovnikov over the other. So it is regioselective. Now the question is it stereoselective? So if A is the major product, did I create two chiral centers? On the major product here, are there two chiral centers? Yes? Okay. So does hydroboration oxidation go 100% cis or trans? Yes. Did this reaction create a major product with two chiral centers? Yes. So this reaction is not only regioselective, it is also stereoselective. And I have to put a caveat in here. It is regio and stereoselective in making the major product. In making the anti-Markovnikov product, it is regio and stereoselective. The reason I have to say that is because what about the Markovnikov product? In making the Markovnikov product, was the reaction stereoselective? Why not? Does anyone want to provide a friendly amendment to that answer? How many chiral centers are in that molecule? Don't worry, everybody falls into this trap the first time. There's 0 chiral centers in that molecule. That's why I ask it, to remind us of the fact that if you don't believe me, let's do RS. So what's number 1? OH. What's number 4? CH3. CH2 versus CH2. CH2 versus CH2. They end up in the same place. So there's no chiral centers. There is never a chiral center on a mono-substituted or a di-substituted ring where the groups are at the same position. If you don't like that, mirror plane. Mirror plane does what? Cuts through that carbon, it ain't chiral anymore. So that's why I asked it. That's why I asked that. Usually people will say 2. There were 2 chiral centers to that one. Remember, bold and dashed wedges don't automatically make the carbon chiral. So when I ask you about regio and stereoselectivity, it's going to be understood that I am asking, it's not going to be understood, I'm going to explicitly tell you, is the reaction regio or stereoselective, or both, or neither, in the formation of the major product? Because for some reactions like this one, it may be stereoselective in the formation of the major product, but not in the minor product. So I'm going to have to say it's stereoselective in the formation of the major product, because the major product has 2 chiral centers, whereas the minor product only has 0. See, I almost did that and said 1. So that's how we can determine regio and stereoselectivity, but you have to do it for each molecule. Because if I would have taken this reaction with the BH3H2O2, and I would have said, okay, how about we do that with the two methyl groups? And I say, what's the major product of this reaction? Also, is it regio, stereo, both, or neither? I have to go back to the rules which say, what am I adding to the double bond? H and OH. Does it matter how I add them in this case? In other words, is this reaction regioselective? Because the alkene's symmetrical, so this is not regioselectivity. So the question is it stereo or not? So I'm going to add the H and the OH. And how am I adding them? Cis. So there would be my major product. Does that product have two chiral centers? This one does. So since this has two chiral centers, did BH3H2O2 add 100% cis? Yes. Did I produce a product with two chiral centers? Yes. This reaction would be stereoselective. So, in order to determine regio and stereoselectivity, we can break this down, eliminate the ones that aren't, and then just look at what's left over. But just the real reason why this is stereoselective is because if I would have added the H and the OH trans, I would have produced the diastereomer of this molecule, and the reaction selected one diastereomer over another, yes, 100 to 0, and that would make it stereoselective.
So I don't know if this might be kind of a random question, but I'm not super sure why, like, sometimes we just automatically write two potential products and sometimes we only write one.
Well, that's a good question. I could very easily have done that here. I could have said, well, our choices are adding the H and the OH 100% cis and 100% trans. And if I would have done that, I would have said, which one's the major product? This one 100 to 0. And then I just would have said, okay, two stereoisomers, possible. Or what kind of stereoisomers are they? Because if they're enantiomers, game's over. It's not stereoselective. They're not, they're diastereomers. And then we would say, okay, they're diastereomers. That's okay. Did I form one over the other? Yes. Therefore, it's stereoselective. So the first way I did it was kind of a shortcut, but I still get the same answer. So if you're doing a reaction, there are some problems in chapter 12 of Top Hat where they give you three reactions, because I know I wrote the answer out for one of them that somebody had asked about. There were three reactions, and it said, which reaction produced a molecule with no chiral centers? Which reaction produced one that was a pair of enantiomers, meaning it had one chiral center? Which one made diastereomers, had possible diastereomers, and that had two chiral centers? So if we just look at the chiral centers in the product, we can really kind of get right to the point of, is it stereo or not. And in that case, I wouldn't need to write the other product. I would just write the first one and look at the number of chiral centers. Okay, we'll mop this up. If there's any questions, you can put them up on Piazza. If you need some get away from family time, I might be answering them. But if you have any questions, or else bring them back on Monday, and we will mop up whatever's left in Chapter 12, and then talk a little bit more about free radicals, Mary.
Where did you say the practice problems for this were?
The practice problems of these cyclohexene methyl, they are in the Friday, it's not last Friday, it's the Friday before that. And they won't be there once I move them to today's folder.
Okay, so today.
So I'm moving them to today's folder once I get upstairs. Okay? But if you have any questions, email me. Put them up on Piazza. I will answer. Otherwise, have a good break.